Welcome to my YouTube channel. In this video we are going to be looking at the one-dimensional time independent Schrodinger wave equation. In this video we are going to consider the zero potential. Okay, so the equation, the one-dimensional Schrodinger wave equation is giving us this, where here is the psi, which is more or less like the wave function, is a one-dimensional wave equation, right? Then we have Planck's constant all over 2 times the mass of the electron, or mass of the particle. This is the energy. So to solve this particular problem analytically, we send this part to this part. 2m comes here, h bar squared goes down, and minus comes here, and we have this equation. So from here we get to this point, making this one stand alone. We can send this one back to this part, and it gives us this. Okay, to solve this particular problem, we recognize that this equation has the form of takes the form of the Helmholtz equation, and because it takes the Helmholtz equation, we have to replace this one with a constant which is called k squared, or whatever, lambda squared, or any kind of constant squared. So we replace with k squared equal to this, and in that case we have this expression. So we can see we've replaced this one with k squared. So this is a typical structure of the Helmholtz equation, and this equation is popular, and it has a solution of this form. The solving of this equation is in one of our previous videos. You can always visit that video and watch the complete solving. So the solution of this equation is given by this expression. Sometimes it can be represented in the form of an exponential curve and an exponential formula, but we can also leave it in this form, right? So what we want to look at is to apply certain conditions to determine the constant A, constant B, and constant K, because these are 3 unknown, or 3 constant to be determined. So these are the boundary condition. Because the particle is moving along a straight line, so we can start by saying once the particle is at the initial position, the wave function is 0. Once it has gotten to the final position, then the wave function is also equal to 0. So applying these 2 boundary conditions, let's see what and what can be determined from these 3 constants. So let's apply the first one. When x equal to 0, our phi equal to 0, and that gives us, at x equal to 0, phi equal to 0, and that gives us a cos k 0 plus b sin k 0. Sin 0, because this one will give us, sin 0 will give us 0, everything will disappear. Cos 0 will give me 1, and that leads to a equal to 0. So we have this expression. So just by applying the first condition, boundary condition, we have gotten a equal to 0. So let's apply the second condition. That's wherever we see x, we replace with L. But before then, we can go back to this original expression and rewrite it without putting this a, because a is already 0. So we have phi equal to b sin kx. So our wave function will now reduce to this form. So we can now apply our second boundary condition, which is x equal to L, and that leads to phi equal to 0. So we have this. Now that we have this, we can rewrite it in this form, that 0 equal to b sin kl. Now we now have 2 parameters, b times this equal to 0. So one of them has to be 0. And from logical conclusion, b can never be 0, because if b is 0, take note, a is already 0. If b is 0, then wave function will be 0. So that will not make sense. So instead, sin kl has to be 0. And if sin kl is equal to 0, we need to find out what are the parameters, or what are the values of this expression that will make sign equal to 0, and that will lead to KL must be equal to n pi. If you look at it, if I put 0 here, sine 0 is 0. If I put 1 here, that is pi, which is 180, sine 180 is 0. If I put 2 pi, which is 360, sine 360 is 0. If I put 3, 4, 5, so that means for this part to be 0, KL has to be equal to n pi. From here, I can make my K the Soviet formula, which is also a constant to be determined, and that gives me K equal to n pi over L. I can now substitute K equal to n pi over L in this equation, and that gives me phi equal to summation of Bn sine n pi x. Take note that since we now have n where n runs from 0 to infinity, for every value of n there should be a corresponding b. So that's why we have b subscript n summation. So now that we have this expression, the next thing is to determine our bn, right? And to determine our bn, we use the normalization expression, and the normalization expression is given by this x, where phi star is the complex conjugate of phi, and when we normalize this expression, it should be equal to 1. So let's go and write this expression out for our phi, and that gives us this part. So we've dropped our summation, which might not be needed now. So this part is the wave function. There is no complex sign, so this one and this remains the same. So if we simplify, it gives us this expression, bn squared sine squared n pi x all over L dx equal to 1. We can take bn squared out because it's a constant, and that gives us this part. Now when we integrate these parts, right, this part is going to be equal to L all over 2. L all over 2. The working is not shown here, but it can be shown. You can always fall back on some maths textbook on how to integrate sine squared n pi x over L dx, and that gives us b squared n L over 2 equal to 1. So I can send my 2 here, send my L down, and make my b the Soviet formula, and that gives me b square root of 2 over L. I'm dropping my n because this is the only value. There is no longer n here in this expression, so no need to put n here. So b is now equal to square root of 2 over L. We can now go back and substitute it into this expression, and that gives us phi equal to square root of 2 all over L sine n pi x all over L. This one is called the normalized wave function. Also, since we have found out our k squared to be equal to n pi L squared, and which is equal to 2me all over h bar squared, we can make our E Soviet formula in terms of this one. We make E Soviet formula when you equate to this one, and that gives us E equal to n squared pi squared h bar squared all over 2m L squared. This is the energy of a particle, free particle, in quantum mechanics. I hope this helps. Please like, share and subscribe to this channel. Thank you.